Hey everyone, welcome into this lecture on the integration by parts. In this lecture we're going to talk about a computational algorithm that you can use to kind of save yourself some writing when you compute integration by parts. Now before I tell you the algorithm, I'm going to caution you. You need to know integration by parts, you need to know the formula, you need to know why it works, you need to be comfortable using the theoretical formula for integration by parts. But this computational table that we're going to build here, table algorithm, can be useful, okay? It can be useful. So let's first start by asking this question. Let me write down the formula for integration by parts first. Remember, the integration by parts formula in kind of simplified symbolic form is the integral of u dv is equal to u times v minus the integral of v du. And remember that one of the most kind of important choices that you have to make when you try to use the integration by parts formula from the very beginning is what are you going to choose to be your u and what are you going to choose to be your dv, right? So I'm going to rephrase this question as how do we choose u, okay? All right, so we'll go through this and then I'm going to actually rephrase it another way that might help us remember it a little bit better after we do this. But how do we choose u? Well, we know from our previous examples that we've seen that the choice of u is going to be made so that when we move the derivative, this derivative is going to move from v over to u, right? The derivative was on v over here and it moves to u. And so as we choose u, we want to think about what is going to make our equation easier to solve, right? Our integral easier for us to compute after taking the derivative. So how do we choose u? Well, there is a made-up word. It's kind of, there are different ways to write this word. So I'm gonna write this word this way, and then we're going to actually turn this whole situation around in a second. But there's a made-up word, which I like to read as liate. Some people read this as liate, but I put a little accent here. So liate reminds me of coffee. Actually, the accent should be here if it's liate, right, for coffee. So we think of coffee. And then this is going to tell us how to choose our u. So we'll choose our u going down this formula, or down this fake word. But for that to be useful at all, we have to know what these letters stand for, right? So the letters stand for, first of all, logarithms. So if we have a logarithm as one of our functions in our antiderivative, or our integral, we're going to choose that to be u, always. The I stands for inverse trig functions, and this could also stand for inverse hyperbolic trig functions. All right, so inverse functions, hyperbolic trig or trig, arc functions. The L kind of stands for algebraic, I think, but really this is almost always going to mean polynomials. All right, could mean rational functions in very special cases, but algebraic. T means trig, and now we're getting into the zone where it's not really ideal, okay? So trig functions, when we choose a trig function to be u, we take the derivative. If we think specifically of sine and cosine, those are in a cycle, right? So they repeat in a cycle of 4, but they always come back. So you've got some kind of periodic situation going on if you're down here in the trig situation. And then E finally stands for exponential, and these are the worst ones to choose for u because when you take their derivative, nothing happens, right? The function, you might multiply by a constant or something, right? But it doesn't actually it doesn't change the function itself. It changes the constant, but not the function, right? So this is how we choose u. We go down this list: logarithm, inverse trig, algebraic, trig, exponential. And if you're left at this point where you have like 2 exponential functions, you probably want to use a different way. Integration by parts is not your ideal method at that point. But anyway, so this is the chain of events here for choosing u. Now, it would be really nice if this was a real word, right? And so whenever we choose u, we automatically get dv, right? Because dv has to be the rest of the integral. So you could rephrase this question as how do we choose dv, right? And so obviously if the choice of u is going to go down this list, the choice of dv would go up this list. But guess what? When you add in a dv, you're adding a d, a differential, right? So you choose your dv by turning this list around, and then you can drop the accent because now you have a real word, right? You choose your d by going down this list, detail, okay? So you're going to choose your dv first to be an exponential, exponential. Then if that's not there, you choose a trig function as your dv. Finally, or next, you would choose your algebraic or your polynomial, right, to be your dv. And then your inverse trig, or inverse or hyperbolic trig possibly here. And finally, your logs would be the last choice of a dv. All right, so your choice of dv actually spells a word. It spells this word detail, and I really like it this way actually. So I know I started off writing it the other way, but this way is easier to remember, I think. So we'll go down the list, down the detail list. All right, so let's try to use this method to choose our dv as we move forward with a couple of examples. I have 2 examples for us, and we're not only going to use this method, we're going to build a table as well. And the best way to show you how to use the table is to just do it. All right, so in this example here, we have a polynomial, x to the 4th, times an exponential. We've already done a few exponentials, right? So this is definitely going to be our dv. We choose, our dv to be the exponential function, and the dv always comes with the dx. It's a differential. It always comes with dx, right? What does that leave then? Well, that leaves the x to the 4th to be the u. So here is an algorithm that you can use to compute this. You have to be very careful as you go, okay? But what I like to do is start with a u column and a dv column. Now what we write in dv is actually, well, we'll see. So we're going to fill out in our u column first, we're going to write our function u, x to the 4th, and then we're going to take some derivatives, okay? So x cubed, this would be 4x cubed, take the derivatives correctly, and then go down this, so this is then going to be 12x squared, 24x, 24, and eventually this goes to 0. So because this is a polynomial, I know that eventually, if I take enough derivatives, it will be 0 eventually, right? In the dv column, I am now going to take just the function part of the differential, so e to the 3x, and I'm going to integrate it each time. Find the antiderivative. So over here, you're taking derivatives. Now for each derivative I took, I'm going to take an antiderivative. So this is going to be a 1/3 at each step, right? 1/3 e to the 3x. Next one, 1/9 e to the 3x. Next one, 1/27 e to the 3x. Next one, 1/81 e to the 3x. And then finally, 1/243 e to the 3x. All right, and so now here's what we're going to do. We are going to multiply on the diagonal these back and forth. We're going to like shoestring this back and forth, multiply these together, okay? And so when we go this way, we're going to multiply, and then we're going to turn around and we're going to come back. That's going to have to, we're going to multiply and add it, right? Add those together. Then we're going to turn around and come back. That's going to have to be subtracted. Then we're going to turn around and come back, multiply, turn around and come back, subtract. So when I say multiply, I mean add, right? And then add again. And then finally at this last step where you have a horizontal, this is going right to left, so that's going to be a subtract, but notice there's a 0 there, right? And this is the one that always comes with an integral. So if it's horizontal, it comes with an integral. So diagonal, you just multiply these up. You add the ones that are left to right, blue. You subtract the ones that are right to left, including this one, green, all right? But the green always comes with an integral. And so let's write out the answer to this, okay? So this is going to be the integral. X to the 4th, e to the 3x, dx equals, now very carefully multiply this all together, right? So it's 1/3 x to the 4th, e to the 3x, minus, because we're going right to left, minus 4/9 x cubed, e to the 3x, plus, because we're going left to right, 12/27 x squared, e to the 3x, minus, right to left, 24/81. We're not going to reduce any of these, so don't worry about that. This is x, e to the 3x, plus, right, plus this way, 24/243, e to the 3x. And then technically we have a minus the integral of 0, right, times 243, e to the 3x. And now your dx comes back. The dx is not visible, but this d here reminds us that there's always a dx, right? Now, I write this because in general, this might not always end with a 0. But this one did end with a 0. So at that point, we know that's just, or that's gone, right? That's 0. And so our answer is all of this. I'm going to pick it up and move it because I don't want to rewrite it. But our answer becomes all of this. But then because it's an antiderivative, it's always plus c, right? And so there you go. There's a table method for, actually, we computed integration by parts 1, 2, 3, 4 times. All right, we integrated by parts 4 times there. You'd have to do it by hand 4 times and be very careful about it, which is fine, right? It's feasible. But the table helps you, the algorithm, I should say, helps you do this without having to write out every single step. Now, if you're going to use this algorithm, you have to make sure you understand and you do it right, okay? So right to left, add, left to right, subtract. If you end up with a horizontal that's not 0, you have to integrate that still. All right, you still have to integrate that. So let's do one more. Let's see, maybe this one won't be so crazy. This is the integral of x squared log of x dx based on our word detail, right? So let's write it out. Detail. We're going to choose our dv to be, there's no e, there's no t, right? Let me cross these off. There's no e, there's no t, there's an a. Remember, algebraic functions, right? Algebraic functions or polynomials, they get chosen to be your dv. And then once you've chosen your dv, whatever's left, that has to be your u. All right, so the algebraic function ruled. The d reminds us that that's our dv. And so now we make our choice, right? So when we make our table, we have our u, we have our dv. Now for this table, the u is the natural log. And let's just take one derivative of this one, okay? So the derivative of natural log is 1 over x, right? With our dv, what do we have? We have x squared. We have to integrate that, right? So x squared integral is 1/3 x cubed. And when this table is only a 2 by 2 like this, actually this is the same as what we did before, but it doesn't matter, right? So let's apply it, right? So what's our antiderivative going to be? Well, it's got to go this way, right? That's going to get added, and then we have to go this way, and we subtract with our integral symbol, right? So we get, at this point, what? The integral, I'm going to rewrite the whole thing here. Sorry. We get that our integral of x squared, natural log of x, dx, is equal to 1/3 x cubed, natural log of x, minus the integral of 1/3 x cubed times 1 over x. And then remember, this one technically has a dx with it, right? So dx here. This still needs to be integrated, but look what it is. It's something we can do. 1/3 x cubed, natural log of x, minus 1/3 can come out. The integral here is just of x squared, dx. X cubed over x is x squared, and we're almost done. So this becomes 1/3 x cubed ln of x minus another 1/3, so that's going to be 1/9 altogether, x cubed plus c. And so that's the answer to this antiderivative, x squared log of x dx. All right, see you guys in the next video.